So our book is laid out in a series of sections: introduction, the living world, biological and human populations, earth systems and resources, and so on. And those are very similar to the environmental science course descriptions that you see in the ACORN guide, the college board booklet that you're given that outlines the course. And we've color-coded our chapters. So chapters 3, 4, and 5 are in light green. And then if you could flip over the end of the book, I don't know if this will show up on this little camera, I doubt it will, but that part of the book is coded green. And it seems to be useful for instructors and for students to be able to access the different aspects of the book from the edge of the binding. You can see that we have a series of things. This is what's circled here at the beginning. Each chapter concludes with preparing for the AP exam. So that's where we have our multiple choice questions and our free response questions. There's also a couple of other features that appear periodically, such as science applied, and we'll take a look at that. And that's taking the science and applying it to some sort of a policy or some sort of a broader societal question. So that in a nutshell is what our book looks like. And for today, I thought I'd start with a very controversial subject that's in the news a lot right now, and we're not going to answer this. This is probably a lot more than you can do in a half an hour. But I just wanted to bring up that really this whole question about obtaining oil from tar sands, right now we're talking about a lot of this from tar sands in Alberta and Canada, and extracting those tar sands and then sending them by pipeline down through the United States to the Gulf Coast, where they would be refined into a variety of petroleum products. And one of the statements that made is obtaining oil from tar sands is much more energy intensive than obtaining oil from oil reserves in the ground, liquid petroleum reserves in the ground. And there have been a series of editorials and op-ed pieces. Here's one that showed up in the New York Times last week: game over for the climate. I think that's a pretty strong statement, and this is a scientist, James Hansen, who makes it. Global warming isn't a prediction, it is happening. That is why I was so troubled to read a recent interview with President Obama in Rolling Stone, in which he said that Canada would exploit the oil in its vast tar sands reserves regardless of what we do. And so this is dealing with policy, but the statement and the underlying premise that Hansen and others is using is that extracting the energy from tar sands will require much more energy, the energy embodied to get that fossil fuel energy out, than conventional oil, and it will release much more CO2 than other energy sources. And to answer this, you need to do a life cycle assessment. You need to do whole system analysis of the whole system of extracting how you get the energy out of the ground, how you transport it, and then how you use it and what happens afterwards. And as I said, this is a really complex problem that would be too hard, I think, to take apart in a half an hour or so. But what we'll do is we'll do some pieces of it. And I just bring this up as one of these long, perpetual questions that is a real challenge, but it's also maybe something that gets your students very interested. So in all of this, what I've just been saying, systems are essential, and I think you'll find that systems appear throughout our book, and systems aren't always treated as uniformly across some of the other books. What is a system? A system is a set of interacting components where a change in one part of the system affects many others. I couldn't get it out of using the word in the definition. Sorry about that. We define that right up in Chapter 1. Chapter 2 is called Environmental Systems. And we go through the monolake system with inputs and outputs, and we have a smaller do the math box that allows students to calculate the input of water and the input of salt to a hypothetical lake that's just 1,000 liters in size. And we make some statements in Chapter 2. The largest system that environmental science considers is Earth. The Earth is a system. Sometimes people say considering the Earth as an ecosystem is one of the practices in environmental science. And in systems, matter and energy are important flows to understand. So we're concerned with the flows in and the flows out of matter and energy to our planet or to individual locations on the planet. In Chapter 2, our first example of showing how there are different systems, and systems are defined by the user, by the student or by the instructor. To a physiologist, a cod is a system. So just one fish could be the entire system to a physiologist. To a marine biologist studying studying the interaction between a predator and prey, then this two-species interrelation is a system. An oceanographer might consider the ocean currents and physical abiotic parameters and their influence on a biotic population, fish. So that might be a system, and so an oceanographer might include all of this in a system. And to somebody who's a fisheries manager, they might be interested in multiple fish populations and human activities and the shoreline and the input of pollutants from the shoreline and the extraction of materials, and you get the idea. So these are 4 different systems, each defined by a different user, by a different kind of scientist. And that's one of the points we make very early on in Chapter 2. Oftentimes in environmental science, we define systems by drawing boxes around them and putting arrows. And so again, it's the user who defines this. So one possibility is to define a system as your vehicle. If you own a particular car, you're looking at the energy inputs, such as the chemical energy in gasoline coming in, and you might look at the useful work that the car does and waste energy in terms of heat from friction in the engine, on the tires, on the brakes, and maybe some sound energy. And so this is a simple box model that shows some inputs and some outputs. And very often that is limiting yourself and limiting your understanding, your analysis, to just include this. So we might want to create a larger system that goes way back here to the left and off the screen that talks about where did the fuel come from, where did the gasoline come from, and how did we get it to be able to put it in the gas tank. And in the same sense, we can talk about outputs, such as what happens to the car when it's no longer useful and it has to get recycled or disposed of somehow. So again, the point is that we define the systems by drawing boxes around things. And sometimes one person's analysis of an environmental question can come out very differently because he or she defined the system differently. So those are the kinds of things that we need to be thinking about.